Yeah. So I'm not jet lagged, but I learned one thing today. It makes no difference when you're giving a talk. You're not more relaxed when you give a talk. So anyway, yeah, I can see that most of you are quite tired. I will make this as down to earth as possible. But before I begin, first and foremost, I'd like to thank you again for coming. This is a really nice meeting. I see many nice questions being asked, and hopefully this is the start to something more significant. I hope to have more such meetings. And also maybe hope to see more of such meetings elsewhere in the world, where then I'll be jet lagged and then maybe you're not. Yeah, okay. So some of you might have heard this in Durham, just some of you. But after that talk that I gave in Durham, I understood some things a little bit better. So there's some refinements to the slides. So well, that may interest you a little bit more. For the rest who are here, we have a combination of mathematicians, mathematical physicists, mainstream string theorists, string mathematicians. So you would find various pieces of this talk interesting to you, but we'll all tie them together in a very nice way, and that would allow us to understand little strings and the M5-brane a little bit better without using recourse to a Lagrangian, okay? Which we don't have anyway. So my title of the talk would be From Little Strings to M5-branes via a quasi-topological sigma model on loop group. I will explain what I mean by all these terms. So the outline of the talk, first I'll give an introduction of the subject and some motivation as to why I want to study this. And then I will give a gong show of the talk. Okay, I think that's important, right? So in case, along the way, you're tired, you've lost your concentration, you would know what the main results are. Okay, so then you get back to the talk and focus on what you should be paying attention to. Okay, so I think that's important. I'll give you a gong show of the talk, summary of the results, and then I will go to the main body, which explains those results. And of course, I will conclude and talk about some future directions which we can take along these lines. Okay, so introduction and motivation. So in this talk, very specifically, we will discuss a quasi-topological twist of a 2D n equals to 2 nonlinear sigma model on CP1 with target space the base loop group, which we will denote as omega SUK. Of course, we could generalize this to other groups, but for the purpose of studying a stack of KM5-branes with no orientable planes such that the gauge symmetry in lower dimensions, this has UK, we would concentrate on such a base loop group. But it works for all G, general G. So the motivation for looking at this model, I'll explain what quasi-topological twist means. The motivation for studying this model is, as I mentioned earlier on, to understand a little bit about the string theory and which part of it, the ground and half-excited states of the six-dimensional AK-1 n equals to 2, 0 little string theory. There are many little string theories. There are 1, little string theories. Essentially, these are the string theories that live in the NS5-branes of type 2A or type 2B theories. Okay, and we are looking at the little string theories that live in the NS5-brane of a type 2A theory. So that's a 2, 0, 1. So we're looking at not just the ground states, but the left excited states also. Okay, so that's where the quasi-topological nature of this sigma model can allow us to compute or to understand the half-excited states of this string theory. Now the ground states themselves, which in some sense is the point particle limit of the little string, that gives you the 6D 2, 0 theory, okay, which we have seen a lot so far in the past 2 days of talks. And from our analysis, we would be able to say something about that also, and to connect with some results in geometric Langlands correspondence, but not for complex curves, but for surfaces. I'll explain what that means. Okay, so the bottom line is that the 2, 0 theory, from the 2, 0 theory, understanding that there's some connections to generalizations of geometric Langlands from complex curves to complex surfaces. And that will serve, in some sense, as a mathematical verification of our physical results, physical computation. Okay, so I will say more about that. Okay, so that leads us to the second point. Okay, so this is what I was saying just now. From here, we would be able to derive, okay, in our physical computation, we would be able to derive purely physically this geometric Langlands correspondence for surfaces, which was first defined by mathematicians Braverman and Finkelberg. Okay, and also present a generalization of that correspondence. Okay, so if you will, a half-excited generalization of that, and we would see what that involves. Just to go forward a little bit, if you look at the Bravo-Finkelberg conjecture, it involves cohomology classes on the moduli space of instantons on R4. And then on the other side of the correspondence, you have affine algebras. And in the generalization, whereby we are looking at the physics of the half-excited states, we won't just get normal cohomology classes. We get these things called chiral differential operators. Okay, so in some sense, they are higher dimensional extensions of the RAM complex. Okay, so if you look at this chiral DRAM complex, this chiral differential operators, and they're graded by dimension. In dimension 0, they give you normal cohomology classes. So for higher non-zero dimensions, they give you these things called chiral differential operators. They're just mathematical objects which generalize normal cohomology theory, DRAM cohomology theory. Okay, and then on the other side, you get a toroidal algebra. So not an affine algebra, but you get a toroidal algebra. So you have indices which denote these higher excitations. So you would have currents that don't just contain like an M, just a Laurent expansion index. You have two indices, and that will give you a toroidal algebra, as we will see in detail later on. And from this study of the little string theory, we can say something about the M5-brane. Okay, we can say something about the half and quarter BPS sectors of the M5-brane through this connection of M2-branes, ending on M5-branes, wrapping an 11th circle, and that description of the M5-brane. Okay, and we will. It's quite interesting, and we will see some very nice results coming up from there. So this talk is based on a paper that I wrote with just too many people. I mean, my postdocs and students. One of them is here, Mia Ashwin Kumar. So after the talk, if you have any questions, you can ask me or you can ask him. Okay, so it appears here in Nuclear Physics B, and it's built on some earlier insights that I did, work that I did from over many years. So it's these are the papers, and also some crucial insights from this review. It's a review of the old sort of analysis of the 5-branes, which I felt deserved to be revived. Okay, there was a long time, there's very nice work that was done in the late 90s on 5-branes and M theory. And so we relooked the results, relooked the insights from there, and we decided to give it a modern twist, modern version, modern interpretation of those results and generalizations and more insights using this sigma model on loop group. Okay. Now, to summarize the results, so in this quasi-topological sigma model with target space base loop group as UK, there is a scalar supercharge. After you twist it, the supersymmetries, some become vectors, some become scalars. There are two ways you can twist it. For an n equals to 2, supersymmetry, you have two U1 currents. There's a vector and axial one. So twisting just means that you redefine the spins by shift of the charges of the fields either under U1, the vector currents, or the axial current. Okay, so there's an A twist and a B twist. We will do what is called an A twist. And the reason why we choose an A twist is because we want the path integral to localize on configurations that are holomorphic maps from CP1 into the base loop group. And the reason why we want to do that is because we want to exploit a result by Atiyah, a very nice result, purely mathematical result by Atiyah that relates the moduli space of instantons on R4 with holomorphic maps of CP1 into the base loop group. Okay, so I'll explain how that comes in handy. So summary of results, so you have this scalar supercharge here, which generated supersymmetry survives on the CP1 world sheet. It's a scalar supercharge, it's got no geometry, so it's insensitive to the curvature of the world sheet. Whereby in the Q cohomology, so if you're looking at things which are annihilated by the charge, but cannot be written as a commutator of a charge and something else, okay, then you realize that you have these, you can derive this algebra from a residue of the OPEs of these operators in the Q cohomology. So if you look at these currents, they are not dimension 0. They're dimension 1, right? They're dimension 1 currents, okay? And as I said, in a quasi-topological model, you can have things which are not just dimension 0. You can have higher dimensions, holomorphic dimensions, okay? So these operators are allowed. In the usual case where you're studying the topological sigma model, the A sigma model, the B sigma model in quantum cohomology and all that, that's only dimension 0, because those are topological models. This is a quasi-topological model, so it admits in its Q cohomology operators that have holomorphic dimension positive. Okay, so this is one. And so what happens is that if you compute the Q cohomology, you can see that there are operators which obey, okay, an OPE, which residue, if you take, gives you this algebra here, and it's a toroidal algebra. But in the topological sector of the sigma model, meaning if you look at the dimension 0, which is still admissible, then it gives you just an affine algebra. You have operators that are just generating an affine algebra. Okay, so these are the two things that we have, these results. Now, so via theorem by Atiyah, which I mentioned, which identifies the moduli space of instantons on R4 with holomorphic maps of CP1 into the loop group, okay, we can say something about the left excited states of the DLCQ quantization of this 6D AK-1 n equals to 2, 0 little string theory, okay, on R5, 1. Okay, so the connection is it can be described in terms of a sigma model on the moduli space of instantons. And then from there, if you're looking at the spectrum of this sigma model, it can be identified with the spectrum of this sigma model on loop group. Okay, and that's where you can extract the spectrum of the sigma model on loop group and to apply it to the spectrum that you're looking for in the little string theory. Okay, so that's the strategy, right? So what you find is that the left excited spectrum of the string, of this string, little string theory, it's given by modules of the toroidal algebra. Okay. And likewise, the ground states of this little string theory will be given by the modules of the affine algebra. So there's almost like a one-to-one correspondence, right? Okay, so it's very, very neat, very elegant, and it's straightforward, actually, very straightforward. So an offshoot is that the results which we presented in the previous slide here that we got, okay, interpreted mathematically, okay, for the ground state one would be this result. Now this is just the Braverman-Finkelberg relation. So I see mathematics as a lab. For me, it's a lab. Okay, so in the absence of technology that can help us verify the arguments we use in string theory and in our physics, I see mathematics as a lab. So if I find some corroboration with some mathematical identity that was proved in a totally different kind of way, I see that as an independent verification of our results. And indeed, we actually can derive this result by Braverman and Finkelberg. So it looks complicated here, but on this side is just some cohomology, intersection cohomology. Why intersection cohomology? As Neil had mentioned, the modular space itself is singular. So to define it well, to define it properly technically, you need intersection cohomology here on this side. And then here is just the module of the affine algebra, which is like the same thing we saw earlier on in the previous slide. Okay. And then, of course, that we have a generalization of this result. Now, this has not been done in the math literature. But if you look at the half-excited states of the low string, then we would have this instead. Okay. So this is the check cohomology of the sheaf of Caro-Durham complex on the moduli space of instantons. Okay, and on this side we have here a module of the toroidal algebra. Okay, so instead of the affine, and then it's toroidal. So it's quite straightforward. You can see you extend excitations beyond 0 on one side, then you add a loop to the algebra on the other side. Okay, so yes. Yeah, so from a physics perspective in string theory, I mean, string theory is well behaved in orbifolds, on orbifolds too. Okay, so and here we are actually also dealing with the low energy spectrum of things, which means that the singularities are not catastrophic from a physical point of view, but they need to be dealt with mathematically, of course. There are many ways you can do that. Non-commutative deformation, that's one of them. So and a few other things that you can do. Yep. Yes. No, we are. No. We are dealing with quasi-topological. I will write down the explicit thing. It's a usual thing, like in the usual case of Witten, you write down a sigma model, you twist it. So, but we rewrite it in a way whereby it's a Q commutator of one of the superchargers, not the combination of both. In the usual A model, you have like Q plus Q minus, and that becomes QA, for example. So now we can recast this as just Q plus bracket something with some other terms that will not affect our analysis. So it's a half-twisted model in that sense. Yeah. Okay, you'll see the yeah. Okay, so right. Okay. So this is a novel relation. So we have some offshoot for mathematicians to think about also. So that's the nice thing about this result. And then of course we want to apply what we have understood about the little strings and the spectrum of little strings to the M5-brane. Okay, M5-brane world volume. Of course, there's a very nice connection between the NS5-brane and then the little strings that live in it. I mean, in M theory, the NS5-branes become M5-branes. The little strings become the M2-branes wrapping 11 circle. So that's where through this connection, we can say something about the M5-brane. Okay? So using the relevant supersymmetry algebras, which we will show explicitly, one can show the correspondence between the ground states of the little string and the half BPS sector of the M5-brane world volume theory. Okay, so essentially, the idea is this. You have the M2-brane that's inside. It's a half BPS object, so it's half of the supersymmetries of the world volume survive on the M2-brane worksheet inside the M5. Okay, and so if you look at states which are annihilated by all the supercharges on the worldsheet of the M2-brane inside the M5, then you get the half BPS sector of the world volume theory, because that's 8 of 8 supercharges. Now, then if you look at the states that are annihilated by 4 of the world volume superchargers that survive on the worldsheet, then that's the quarter BPS sector. Okay, so that's the correspondence. All right, that's a rough idea of correspondence. And the thing is, so if you look at the half BPS sector, and using the interpretation of those states via this sigma model on loop group, okay, which is given in terms of representations of the affine algebra, and you count them, you will see that if you write out a partition function of these states, they will take this form. That's a character character function of P, okay, which tells you that it's a cousin of a modular form, and it transforms as a representation of SL2Z. Now, SL2Z, so it means that in looking at the BPS spectrum of the 5-brane world volume theory, you see that there's an intrinsic SL2Z symmetry that's right inside. Okay, and the minute you compactify, okay, this 5-brane theory on a torus, then it becomes manifest as duality in 4D n equals to 4 super Young-Mills. Okay, so that's the thing. The point I'm trying to make is that if you look at the M5 world volume theory, the symmetries that you see in lower dimensions are just sitting inside. They're there. You already see them, in some subset spectrum of the theory. P is just a complex number. So when we wrote out the counting of the states, yeah. So the P, we left it arbitrary. So the minute you put in P as e to the power 2 pi I tau, yeah, and then you see it transform like an SL2Z representation. So the point is that it has the potential, when you define the correct P, to be a representation of that. So when we counted the states, we took P as like a fugacity parameter. That's right. And then to some powers, because there are different sectors of the Hilbert space that we wanted to keep track with a variable. Representations of the affine algebra. Yes, dominant, correct. That's right. That's right. So here, dominant highest weight modules. That's right. That's right. Okay, so that's the interesting thing here. Okay, so seeing these states in terms of representations of affine algebra, we actually see, an intrinsic SL2Z symmetry that's sitting inside, which becomes manifest when you, have a torus. Yes.
You're counting states on the intersection.
Intersection.
Of the M2 with the M5.
No, yeah. So yes, that's right. String-like states. Yeah, that's right.
Sort of have two-dimensional surface.
Yes, but it's not compactified. Yeah,
Right.
yeah, yes. So the point is, the philosophy is, as I'll explain, as you mentioned also many times, there is sort of an equality between the M5 brane and the M2 brane. Okay, that's sort of the philosophy. And so when you look at M5 and M2 brane, that is also, ending on an M5, a stack of M5. So if you look at, my point is that if you look at the dynamics of the M2, it captures the dynamics of the M5. So that's the philosophy that we're taking. Okay. Yeah.
But you will eventually relate P to the modular.
Yes. So to see that it can transform as a representation of SL2Z, then you put in a P that has the form e to pi I tau, then it would transform. But we have not put in any torus.
Tau will be the same as the tau of the complex structure of P.
Yes, correct. So the point is that in 6 dimensions we have not put any torus inside. Okay, the P is just a complex, some complex number. Okay, and then if we put in e to pi I tau, then we can see that it has an SL2Z transformation. So that's why it has a representation of SL2Z. That it's like you have a Lie algebra, and then you say, okay, I want an n by n matrix. Then you have some representation of the Lie algebra. That's my point. Okay, so that's what it means. So the point is that we don't put in a torus, but we see that there is a symmetry that's already there. So that's the point. Yeah.
So when you say the partition function,
Yeah. So actually, when we say partition function, we are just like p to the power n, then a n, and a being the numbers in that level, basically. So we mean that, just counting states. So maybe saying partition function is not exactly, it's slightly misleading, I think. Yeah. Because usually partition function can mean genus 1 partition function, which then therefore means there is already a torus there. So that's not surprising. But we just count, when we say partition function, we're just counting it. Just say, okay, maybe an index would be a better term, basically. Yeah. So, but essentially, we're just counting the BPS states. Okay. Yeah. So it explicitly is just like p to the power of n, where n is some sector with some level, and then an, the number of states in that sector. Okay, and then summation over the dominant weights, the dominant the integrable modules that are identified by the dominant weights, highest dominant weights. Okay, so that's what's going on. And if we look at the quarter BPS sector, okay, which means that's associated of the M5 brane, which can be captured by the left excited states of the little string, and then we do the computation, okay, we end up getting something like this. Okay, we end up getting something like this. All right, so, and why do we have more parameters now, like P and Q? That's because it's a toroidal algebra, so it's got two, sectors now, not just the N, but the M. So we need like two fugacities. Okay. So, and if you look at this thing, it looks like a cousin of an automorphic form, whereby if you put in P and Q, like P again, e to pi tau, Q something else, e to pi something, and then it transforms with, it's a representation of this SO2, 2Z. Now that's, yeah. Okay, that's a T-duality group. So you have an intrinsic sort of T-duality that's also sitting inside. Yeah. So 2 parameters because the toroidal algebra has is divided into 2 parameters of sectors. Yeah. Okay. So you end up having this thing. So there is also intrinsic T-duality that's sitting inside. So again, once you put in the torus, then you see it as the manifest T-duality. So the point, yes. Sir.
Well, the concern would be that in all of these sums to be sort of well-defined in counting the states, you have implicitly put things on a torus to regulate just the continuum nodes.
I mean, what we just did was purely just summing like the numbers and all that. We didn't put it on a torus to regulate anything. So we're just summing a discrete sum of things.
What's discrete? I mean, why aren't they continuous?
Well, because the representations that are admissible, the positive energy representations, the physical ones, are the ones with the dominant weights. So that's finite. Yeah, that's finite in number.
I imagine you put some kind of that statement probably relies on some boundary conditions. Statement that you regularize. I'm just guessing. I don't know.
Okay, yeah. So the point is that there are finite number of them because these are just BPS states. They don't go on forever. They are just quarter BPS states, the left excited states of the low string. Yeah. Okay, so the point is that just like type 2B theory, where you have an SL2Z symmetry there, even without a torus, is something similar is going on here. So the point is that in string and M theory, you have all these symmetries that are intrinsic to the theory, okay, that become manifest when you actually add the geometry inside. So that's what we have seen here and found here. Okay.
But in type 2B, the SL2Z is there even without compact, right?
Yes, correct. So like in this case, there's no compactification yet, but you see the symmetry in the spectrum. Yeah, the point is that the spectrum, transforms as representation.
Here, first of all, the fact that you are taking a trace, right? Means that I think effectively the time direction is imperial compact.
But there's only one like that.
Yeah.
But not.
Other one, I think, as I said, that you must be somehow regulating the spatial direction to make things discrete.
Otherwise, you wouldn't have a discrete spectrum of excitations of these BPS strings.
Okay, so but what we did in our computation was to just count it like, just discretely, and we didn't do any regularization. And we got this. Yeah, that's the thing. And that's because from the representations of positive energy representations of affine algebras and toroidal algebras, they're finite, basically. Yeah. So that's the thing. So the point is that we counted it mathematically. And by the mathematics of these things, there are just a finite number of them. And so it does, we didn't need to implement some kind of regularization to the sum to make it finite. And then that's what we got. Yeah. Okay, so once you add in the T2, and it becomes T duality. So that's the takeaway. Okay. Right, so that's the gong show for the talk. Okay, so if you're tired and if you're not following things, that's basically the main result. Okay, so let's see how we get it. Okay. So just some basic mathematics on loop group and base loop group. So we have a loop group. What's a loop group? A loop group is basically the group consisting of maps from a unit circle to a Lie group. Okay, so you can find this in a very classic book by Siegel, Loop Groups. I think it's the same title, yeah. And then there's this thing called the base point condition. So if you parameterize the group as the S1 as a EI theta, when theta is 0, it maps to the identity, so it's identity map. Then with this condition, you get what's called the base loop group. Essentially, what's important for us is that it looks like this. It's a loop group modeled out by G. Okay, so it is a G equivalent subset of LG endowed with an LG action. Okay, so these things that I specify because you will see that they manifest in the physics. Okay, so if there's an LG action, if you define a string on such a manifold, then you'll see inheritance of this LG action on the world sheet, that kind of thing. So that's where I'm alluding to. Okay, so the loop group, base loop group also admits a closed non-degenerate symplectic 2 form, omega. So that allows us to define holomorphic maps from CP1 into the loop group. Okay, the complex and symplectic structures of the base loop group are compatible and conspire to make it an indefinite dimensional Kähler manifold, which is compatible with 2, 2. If it's a hyperkähler manifold, you need an n equals to 4, 4 sigma model. But if it's 2, 2, Kähler is fine. So a bit more about loop groups. As you can see in the next few slides, they are almost like the ordinary Lie algebra that you see. It's just that you have additional indices. Okay? And the additional indices, you can think of them as coming from the loops. Because the base itself is the group, and that's a Lie algebra index. The loops themselves give you the additional indices. Okay? So if you look at an element, zeta and eta elements of base loop group, of the base loop algebra, okay, which we write as this. So you can write it as this. This is standard textbook stuff from Siegel's book. So you can see the generators of the Lie algebra. They're just here. If you remember, this was the S1. Okay, and these things here are like the maps that link the S1 to the group. Okay, so we just have 2 examples so that we can show the commutators of these things. So you can write this as this. So the n, it takes over integer values because the space of the maps from the loops into the group, that's infinite dimensional. So you have n that counts, to infinity. And a counts from 1 to dimension of the Lie algebra of the group. Okay. So the base point condition, which we saw just now, this being equal to 1, just translates to this. So it's a very simple constraint. Then you can write the metric as this. Okay, so you can see, things which look like a combination of both like a differential geometric kind of metric and the Lie algebra kind of metric. Okay, and then you can also have this commutator here. So it's a generalization of the usual Lie algebra commutator. As I mentioned, you have Lie algebra index, but you also just have the m and n's, and that corresponds to the degrees of freedom of the loop. Okay, so and then structure constants here appear, just that you have this additional thing here. So it's almost the same, just with the additional index here. Okay, so the sigma model that we'll be using is the usual one, n equals to 2, 2. Type 2 string theory, you see such sigma models. The only Oh, you mean there was? I mean, you mean the algebra? Yeah, right. So it's just like that, like normal Lie algebra.
Yeah.
There's no centralism. No, there isn't. Yeah, there isn't. Yeah, there is. Okay, so the action looks like this, so very familiar. So what's different from this action with the regular one is that you just replace the I and J's that you know of a normal manifold with like A's and M's. Okay, because there are two parts to the space. There's the base and then the other loops. Okay, so it looks exactly the same. Right? And then if you have a bar here, it just signifies that we have negative modes on the end. Okay, so we have the same thing. So again, I, J's, and K's in the regular sigma model, you just replace them with A's and M's. Okay, it's the same thing. Okay, now we want to twist the model in the usual way. Okay, so we want to do the A twist, whereby we shift the spin of the fields by one of the U1R charges. There are two, a vector and XO1. Okay, so we want to consider the A twist. And so when you do that twist and you redefine the spins of the fields which are charged under the U1R symmetry are only the spinor fields. So the scalars have no shift in their spins. The spinors have shift in their spins. So they either get shifted to be spin 0 or shifted to be spin 1. Okay, so as you can see here, it's originally spin half, and then it shifts to be spin 1, whereby we can denote it with a z-bar anti-holomorphic coordinate on the worldsheet, which tells you it's a spin 1. And then this will be spin 0, so it becomes a fermionic field with spin 0. Okay, and a few of them here like this. And then you can rewrite the action in terms of these fields. So nothing changes, just rewriting them in terms of the new notation of fields whose spins have been shifted. Okay, and so you can rewrite them in this way. It looks almost the same if you recall from the previous slide. And then you can rewrite it as this. So this is a pullback of the Kähler form on the loop group. Okay, so this is a very standard sort of way of writing a topological A model. Okay.
Why did you add the prefix quasi?
Okay, so I'll explain the next slide. Yeah, the quasi, right. So the point is this: you twist it like a normal topological one,
Right.
but you rewrite it in a quasi-topological way, which I'll show now.
Okay.
Yeah. So that's easy. So in heterotic 02, with the work that you did and the current differential operators, that's the only twist is quasi-topological for 0, 2. That's because it doesn't have enough supersymmetries to be fully topological. Yeah, you're twisting both, but you can rewrite the Lagrangian in terms of one supercharge. Right. Yeah, that's the point. That's the point. So so in the 2, 2 model, there are two ways to write the Lagrangian in terms of the A supercharge with the Q plus and the Q minus 1, the usual one. But you can also write it in terms of just one charge. But you have other terms which would not be relevant to our analysis. That's the thing. We will see in the next slide. Okay, so that's the thing. So the point is that n equals to 2, 2 model has, you can look at the QA cohomology, or you could look at the Q plus cohomology. So you could. And you could compute things which are only in the Q plus cohomology, because the Lagrangian, you can rewrite the Lagrangian in a way that it's a commutator of just the Q plus with some other terms that don't matter. Yeah. So that's the point. Right. Yeah. So the way to understand this is also, if you look at the heterotic sigma model, which only is quasi-topological.
Well, there you go. There you only have.
Yep. Yeah, one. Yes, half twist. That's right. That's half twist. But if
You
you
can take this model and only do a half twist.
yes, yes. That's right, that's right, that's right. We could do that, okay, but it still works here, but because we can rewrite it in terms of just one supercharge. You could do a real half twist where it's only twisting for one of the supercharges, instead of two. But if you do it two, and then, because the point is when you do it two, the bosonic zero modes would give you the holomorphic maps, and that's what we need. That's the point. The point is we want the A model. We want the A model so that the zero modes will be like the A model ones. But yet we want to just look at the cohomology of just one of the supercharges. That's the point. Okay, so that's the point. Okay, so and to understand why this is possible, if you look at the heterotic sigma model, which is only a half twist because there are just two supercharges, okay, and you can only twist by one. If you look at the gauge bundle, at the tangent bundle, at the point where the gauge bundle becomes a tangent bundle in the heterotic sigma model, that becomes a 2,2 theory. So at the tangent locus, at the tangent bundle locus, that becomes a 2,2. So then in that sense, the half twisted was already sitting there. And then when you put a tangent bundle inside the thing, then it allows, so that's where the half twist is still possible in the 2,2 model. So that's sort of a heuristic way to understand this thing. Okay, never mind. When I write out the thing, you can see. Okay, so anyway, we did an A twist, so there are basically two nilpotent scalar supercharges, Q plus and Q minus, okay, which, and if you look at just this supersymmetry, so we're interested only in this supersymmetry, then it's these things here. Okay, so very nice. This is very important here. This is what we want, okay, as we will see later on. Okay, so the point is this. We can rewrite the Lagrangian in this form. Okay, it's not so well known that you can do that, but you can. Okay, you can actually do that. Okay, so you can rewrite it in terms of a Q commutator of just one of the supercharges with something here that contains the metric of the target space, which we can append with a scale, and that will determine the coupling of the sigma model. Okay, and then we have terms that are dotted here, which in ellipses, which are metric independent, but depend on the complex structure of the target space, but then there's no metric inside, okay? And then, of course, the instanton term here. Okay, this n is just the degree of the map of the pullback of the symplectic form from the loop group onto the worldsheet. Okay, so, and then if you compute the stress tensor, okay, you will realize, okay, so the usual way, del S by del GZ. Now, this stress tensor, the holomorphic stress tensor, is Q plus closed. But now it's generically not Q plus exact. Okay, so that's the difference. But the anti-holomorphic stress tensor, that is always Q exact. That's Q plus closed and it's always Q exact. You can always put it in a Q plus exact form. So if you consider correlation functions in the path integral, whereby it's only annihilated by this Q plus supercharge, but are themselves not written in a Q plus exact kind of way, then you would see that that correlation function itself, okay, is not completely independent of arbitrary deformations of the metric. So for that to happen, it means that for any variation of the action for any component of the metric, that has got to be zero. And that means that any variation of the action with respect to any component of the metric has always got to be Q plus exact. But that's not true. It's only true for del S by del GZ bar Z bar. So it's only half topological, if you will. Okay, that's different from the topological sigma model that you usually see. But of course, if you look at this expression, the path integral itself, through a saddle point approximation, would localize onto configurations that minimize this, which are the Q plus fixed points. And if you see from the previous slide, okay, here, if you look at the bosonic zero modes, that tells you that they are holomorphic maps. Okay, right. So they're holomorphic maps from CP1 to this. So in that sense, we are doing perturbation theory around zero modes, which are holomorphic maps from the worldsheet onto the loop group. Okay. So, the reason why this Q plus cohomology has ground and left excited states is because if you look at the operator whose eigenvalue gives you the holomorphic dimension of the theory, it's Tz bar Z bar or Tzz. So Tz bar Z bar gives you, if you take the residue and the first term, that gives you the L0 bar operator. Okay, so because that is Q exact, as we said just now, so things which are in the Q cohomology would mean that they must be operators with eigenvalue which L0 bar equals to 0. Okay, so you have this. So you take this, and then it gives you this thing here, okay, and this one here, okay. So so this one is Q exact, okay. So this is trivial in Q cohomology, okay. Well, this is not. This is not. You can't write it in that way. So you have operators whereby this is 0, but this is possibly greater or equal to 0. Okay. So that's the point. So, and that's how a typical correlation function will look like. So I put in everything. Okay. So the point is that you have operators whereby it's 0 dimension on this side, but positive dimension on this side. Okay. And if it's 0 and 0, then it's the usual. It corresponds to like cohomology classes on the moduli space of holomorphic maps into loop group. Now that's just quantum cohomology. You know what Witten defined in the late 80s. Now, if you look at excitations on the left side, then they are given by the chiral differential operators. Chiral Ram complex on the modular space of holomorphic maps. Okay. Yeah, because of 0 modes, if you put in the fields together, the 0 modes themselves are coordinates and tangent vectors on the modular space of holomorphic maps. So in the 0 instanton sector, they are the target space, but in the non-zero instanton sector, you have the holomorphic maps. The modular space holomorphic maps. Yeah. The modular space of holomorphic maps into the loop group, I think it's not infinite dimensional. It's compact. Yeah. No, not compact. It's not infinite dimensional. It's not. There is a dimension to it. You can have an index to count the thing. Yeah. That's right. So that index also counts the number of Fermat 0 modes that you have. Yeah. Okay. So in other words, you can define a top form in that space. Yeah. So, okay, so if you look at this correlation function, typical correlation function, do a derivative of this inside part here with respect to t. Okay, and you can see that it actually is just an expectation value of a supersymmetry variation, and that's 0 base. Oops, 10 minutes. Oh, sorry. Okay, I've got to go a bit faster because I'm left with 10 minutes. Okay, so all right, so that's with the quasi-topological sigma model. Okay, so now the point is we are having this sigma model on a space which is a G-equivalent version of the loop group. So we would expect isometries of a loop group nature to be inherited on the worldsheet. Okay, and indeed we can find Noether currents which generate symmetries on the worldsheet of this sigma model that are in the Q cohomology. Okay, as I mentioned in the gong show of the talk. Okay, and so these operators in the Q cohomology obey the OPEs like this. Okay, so you can see that in the topological sector where this guy here is also 0, then what you have as a toroidal algebra will become just an affine algebra. Okay, so it's written here. Okay, so of course, once we have these operators in the Q cohomology, we can form states of these operators by acting, their creation operators on a vacuum state. And these things here, these expressions here, you have a map with expressions of residues of the currents acting on 1. That's the usual CFT story. Okay. And so through this correspondence of these operators with what I mentioned earlier on about the Q plus cohomology being the check cohomology of the Carroll-Ram complex on the holomorphic map from CP1 into the loop group moduli space of holomorphic maps, then we get this connection. So the point is that This, we know, is in the Q plus cohomology, and from the physics of Q plus cohomology of sigma models, they will be associated with these spaces. But at the same time, we are looking at this explicitly, which comes from a toroidal current. We know they are modules of a toroidal current. Okay, so we can make this identification. Okay, likewise, we can do the same for the zero mode, the zero dimension sector, and then we have an identification in terms of not the toroidal-RAM complex, but the usual cohomology. But then it will be modules of the affine algebra. Okay, so we are done with the quasi-topological sigma model. Now let's look at the little string. And what we're going to do next is to use the spectrum that we can get from the quasi-topological sigma model to say something about the spectrum of the little string. Okay, so little string theories exist in 6D space-time. They reduce to interacting local QFTs when the string length goes to 0, so it's like a point particle limit. So this little string theory reduces to the 6D n equals 2, 0 superconformal field theory. Okay, that has no known classical action. It's a very rich theory, so we expect little string theory to be at least just as rich. And as I mentioned earlier on, it's also the world volume theory of a stack of NS5-branes in type 2A string theory, whereby the fundamental strings which reside within the branes have coupling go to 0. So bound degrees of freedom, including gravity, they couple, but the string length is not 0, so you still see stringy degrees of freedom. And these are the little strings that we're studying in the NS5-brane of type 2A. Kim Young will say a bit more this Friday on these things and about T-duality, explicit verification of T-duality. So let's look at the DLCQ quantization of this little string theory. Okay, so that's given by n equals to 4 sigma model. So this sigma model is not the one that we studied for quasi-topological. That's a different one. Okay, so it's an n equals to 4 sigma model. Okay, with target moduli space of instantons, whereby k is the number of branes. Okay, and then the n is the units of discrete momenta along the S1 of the sigma model when it's over that sector of the target space. Okay. So, yeah.
Are these hypercalar or with torsion?
Yes, so it's hypercalar, but the moduli space itself, I don't think there's torsion. It's just hypercalar. No, there's no torsion.
These are not Gaussian.
No. Right. So the ground states of the little string theory are given by sigma model states annihilated by all the supercharges of this sigma model. Okay. So they correspond to harmonic forms and thus L-squared cohomology classes of this moduli space of instantons. Now the left excited states of the little string are given by the sigma model states annihilated by 4 left moving supercharges. Okay. The chiral supercharges, and they correspond to check cohomology classes of the sheaf on this thing. So we are applying this sigma model check cohomology interpretation to this 4 sigma model, which is not the one that we studied earlier on. This is just the DLCQ description of the little string. Okay. Now, Atiyah had this very nice result that could relate these two spaces together. So you can see where we're going with this thing now, which is we had with the 2 sigma model that we studied, the quasi-topological one, the space being this, the DLCQ one, the space being this. Okay? So then we can use, and through the DLCQ quantization of the little string theory, being the sigma model on this space, that we can associate these things with the ones that we got on the 2 model. Okay? So both for the ground states and the left excited states. That's the point. And so when we do that, okay, we can just get this basically. Okay, so the ground spectrum of the 6D little string theory gives you modules of the affine algebra. And then likewise for the left excited spectrum of the little string theory, modules of the toroidal algebra. Okay, I'll skip this part. This is the mathematics part. The point is we have some corroboration with some mathematics that was derived in a different way, and for me it serves as a check of what we have done so far physically. Okay, and we have generalizations for them to think about too. And let's describe the M5-brane now. So the point is that we can use, the little strings in the NS5 in type 2A are just like looking at the M5-brane in M theory with M2 branes ending on the M5 and then wrapping 11th circle and seen at an energy scale whereby 11th circle looks small. Okay, so if you have a low enough energy regime of that description, you can use the little strings to describe what's going on with the M5. Okay, that's the point here. Okay, so let me just continue with the talk. So as I mentioned just now, the M5 itself, okay, it has 2,0 supersymmetry with this supersymmetry algebra. So if you're looking at the half BPS states of the world volume theory of the M5, okay, they're looking at states which are annihilated by 8 of the supercharges, these 8. And if you look at the M strings, so now we're in M theory, so the little strings are called M strings now, okay, inside. So they preserve 8 of the 16 supercharges in a 4-4 kind of way, okay. So they have this algebra, so you can count, there are indeed 4 supercharges of this type, 4 supercharges of this type, and they have this algebra of a left moving and a right moving operator here, okay. This gives you the holomorphic dimension, anti-holomorphic dimension of the states, okay. So the half BPS states are the states which correspond to this, the half BPS states of the M5 world volume theory would correspond to the states which are annihilated by all these supercharges because these supercharges were inherited from the M5 brane world volume. So if you look at the counting, so terminology here is 1 and 2, but it's actually AB, which is 3 and 4. Okay, that's inherited from the space-time supersymmetry, okay, in the world volume. So the point is, if you want to look at a half BPS sector of the M5 brane, okay, it's captured by the ground states of the low string theory, which then means that we can count the half BPS states of the M5 brane world volume theory in terms of representations of the affine algebra. And that's what we got to at this point in the gong show. Okay? And and then yeah, we had a discussion on this, and that's where the intrinsic SL2Z is inside somewhere. And then it becomes manifest as S-duality when you compactify on a T2. And then likewise, if you look at the quarter BPS states, so instead of annihilation conditions, there are two lines of that. We have just one line because you have only 4 supercharges that are annihilating the states for quarter BPS. Okay, and these 4 supercharges correspond to the 4 supercharges on the worldsheet, yes. Okay, they correspond to the 4 supercharges on the M string worldsheet on one side. So if you look at states which are annihilated by just 4 supercharges on one side, then they would correspond to the toroidal representations of the toroidal algebra. Okay, so we do that, and we count it, and that's where we got this thing here, which we saw in the beginning of the gong show, and an intrinsic T-duality, which emerges if you have a torus that's put inside. Okay, so to conclude, we've explained how a quasi-topological sigma model on loop group, the 2, 2, twisted one, can be used to help us understand 6DAK-1, 2, 0 little string theory, okay, essentially the ground states and the left excited states. How it can be used to derive and generalize the Braverman-Finkelberg relation, which is about a geometric Langlands correspondence, not for curves, but for surfaces. For the mathematicians who are in the audience, it's just replacing the geometric Satake isomorphism, the curve in one side with a surface. Okay, and they find that it's going to be representations of an affine algebra. So we have done that. And then we have also used the results that we got for the low strings to say something about the BPS sector of the M5 brane world volume theory. So notably, we find that the chiral spectrum of the low string is furnished by representations of a toroidal algebra, and the BPS spectra of the M5 brane world volume theory are closely related to modular and automorphic forms. Consistent with these aforementioned physical results is the geometric Langlands correspondence for surfaces, the Braverman-Finkelberg relation, and its generalization, which we also physically derived. Okay, so as I mentioned here, this serves as a source of a lab for me, if you will. And through this, well, you see a nice interconnection between string theory, little strings, M theory, the M5 brane, geometric representation theory, which is geometric Langlands itself, and number theory, because you have automorphic forms and you have modular forms, or cousins of those things. And future direction, okay, so maybe we want to understand the full spectrum, not just the chiral part, okay, the full spectrum, left excitations, right excitations. So we expect, a tensor product, basically, okay, of a holomorphic toroidal algebra and an anti-holomorphic one. That's something we can guess, the form. We could gauge this loop group sigma model to get a generalization of what is called the AGT correspondence. Okay, so if you're interested, I'll tell you more, but I'm running out of time, so let me just go a bit faster. So of course, we want to go beyond the BPS sector of the M5 brane. That will be captured by the full spectrum of the low string theory. So we expect the corresponding partition function of states to be like what we saw earlier on, but appended with some extra Dedekind function, which represents like excitations on the right side, something like that. But these are all guesses. So we have to check, we have to compute. So that's something which I'm guessing at this point, but it gives us some rough idea of where we're heading. Okay, thanks for listening. Yes, Martin.
Did I get it right? You said it, I thought you said at some point that the sum over the representations, the lambda primes, would be like, it's finite?
Yeah. So those representations, those modules are finite. They have a finite number. Yeah. Because the dominant highest weight representations. And those highest weight representations are the ones that are physically relevant because they have positive energy and not negative energy.
There's an infinite number of
Yeah. So the ones which are positive energy, those are finite. So
you have to fix the level. What's the condition on last finite?
yeah, you have to fix the level, that's right. Okay, so that's something that, yes, that's right, the level is, because I was rushing through it, there was a C1 and C2 somewhere, those are fixed. Yeah. Okay. Yeah, sure.
What is known about representations of toroidal algebra?
What is known about representations of toroidal algebra? Well, I mean, many things. If you're looking at what the math people are doing, physics, of course, we see a relevance here, but then there's work by Nakajima, for example, whereby you're talking about, essentially, higher cohomology theories on the moduli space of instantons, like K-theoretic kind of stuff on the moduli space of instantons. So you're defining things which are like the A-roof genus or the elliptic genus on the moduli space of instantons, and then you can see some connections with toroidal algebras.
They are not Cascodi algebras.
No, you're not. Yeah, that's right.
So
Yeah.
I guess you're getting the plane D algebra because you have the target spaces.
Yes, that's right. Correct.
And that's due to the TS theorem that you have. Could you offer some physical understanding of why we have loop target space?
No, we're using the loop group. You see, the loop group sigma model is an auxiliary model. So the DLCQ quantization is a 4-4 sigma model on the space of instantons. That's a different sigma model. But we're using the loop group sigma model as an auxiliary model, and via our TS theorem, we are able to read off what we can say about the DLCQ or little strings using the spectrum of the loop group sigma model. So what you're asking is there a physical derivation of our TS result?
Right, because that's the reason for this your proposed intrinsic.
Yeah. So we are using the 2-2 sigma model as an auxiliary model. So our ultimate goal is just to unravel, to understand something, to know what its spectrum is about. So we have thought about how you could derive it. Okay, I don't see at this point how you can derive it from the, let's say, look at the M5 brane, and then you see a 2-2 sigma model and loop group appearing. I don't see how this can be done. So we're using the 2-2 sigma model as an auxiliary model that will help us to gain insights into the spectrum from a different point of view. Yeah, that's right.
I think we have to close.
Okay.